Thank you for returning to Learning Image Analysis. Our topic today is identifying large-scale structure in an image. So we'll be returning to this image of bimodal alpha and titanium. From the last lesson, we separated the beta, which is all the bright stuff in the image, from the alpha, which is the dark spaces between the beta. And today, our goal is to separate the primary alpha, which are the large, circular, roughly equiaxed alpha grains, from the secondary alpha, which are these small, thin alpha laths in between the primary alpha. Our learning objectives for today, first is how we're going to use morphological operations to distinguish what actually is primary alpha versus what's secondary alpha. How can we manipulate the segmentation to pull out one and eliminate the other? Of course, then you have to deal with the fact that you've messed with the segmentation, and so there's going to be some errors introduced because of that. And we can use our concept of two-stage segmentation of defining a feature versus distinguishing a feature to accommodate for those errors. Specifically, we're going to return back to our original segmentation to define where the alpha grains are and use our manipulations in order to simply distinguish what those grains are. And then we'll have some segmentation mathematics that we use to actually do the combination, combining the data in those two different segmentations. So here we have our image and recipe from last time with our image segmented into alpha and beta. And our goal now is to separate primary alpha from secondary alpha. So the alpha in green, as you can see, the primary alpha is generally larger than the secondary alpha. And also the secondary alpha tends to be long and thin. So we can use an area threshold, a size threshold, in order to try to make this distinction between the two. And one thing to note is that there's a little bit of pre-processing that we'll have to do in order for that to happen appropriately. So first, our separation of primary and secondary alpha isn't always 100% accurate. There's tiny little joins here and the joins here. And so we can remove these with an erosion. If we erode the alpha away, of course, this join will erode first. And this is going to give us a second benefit as well. Because the secondary alpha is long and thin, the erosion is going to attack it more than it's going to attack these more circular primary alpha grains. So the erosion will help separate primary and secondary alpha and also make the size difference between primary and secondary alpha even more prominent. So let's start here with our alpha and do an erosion. Uniform erosion, let's say 10. How does this look? Our goal is to get the secondary alpha thin or gone without reducing the primary alpha too much. And just off the bat, 10 seems like a reasonable number. It might be honestly hard to tell if this is primary or secondary. If this is primary or secondary, I don't know if I could tell even by eye which it is. Maybe it's primary. But we'll be probably happy with something along the lines of 10. I'm trying to compare this piece to this piece and guesstimating the area that we have. All right, something like that. Okay, and now we can reject features to get rid of our secondary alpha. Reject based on area, say 500. What does that give us? 500 is pretty good. What does 250 give us? These big pieces while still keep removing a lot of these more elongated ones. I think this should, we still want removed 400. Okay, so if we set our threshold here back to 500. Okay, maybe if we can get this distinction a little bit more accurate if we increase our erosion by a hair, say 12. Now, how does the reject features handle this? That is 347, and that is now 153. Yeah, that's a little bit better to my eye. So now if we set 200, 200. What's this one? 345, 210, 225. Again, you sort of have to do the best you can. You're never going to be absolutely perfect, but this looks pretty good. All right. Now, it's tempting to simply redilate this and call that the primary alpha. But really, that's not the best way to do that. If we just redilated by 12, a lot of this fine structure has been lost because the corners, these tips, have been clipped off by the erosion. So instead of redilating, we'll dilate a little bit, clean up, dilate, maybe just say 5, 7, 10. Okay. Again, we don't want to intrude too much on what might be secondary alpha. So say we dilate by 7. And now this is going to be a marker for primary alpha. Remember several lessons ago, I talked about what distinguishes a feature versus what defines a feature. And here we have these markers which distinguish primary alpha from secondary. And then we'll go back to our original and get a different segmentation which defines the edges of this secondary. Excuse me, of this primary. So we take our alpha here, save it away, and we're not going to use memory image 4 again. We can, so we can reuse it, memory image 4, and dilate. We're going to set this to our companion image, call back memory image 4. Now we still got the issue of all these cuts here that we need to make. Because if I'm going to do, say, a keep mutual features between this and this, these need to be separate features. So we'll make all these cuts with a watershed function. Okay, and it's not perfect, but it's pretty close. Okay, if we go to outline view to see if we can see these cuts being made a little more accurately. All right, these cuts are being made, but I'm more interested in cuts through here. That needs to be cut. Let's turn our segment separation a little bit stronger. Okay. Lots of cuts, lots of cuts. All right, so now we have features that are cut off, primary from secondary. And we'll take this now and keep mutual. So that takes this companion image, keeps any features in the current image that are also in the companion. So that removes all this secondary alpha here. And so I'm pretty happy with that then. Now we've got the issue of all these cuts that we made, and we can remove those with a close. We dilate just by one, and then erode just by one. Okay. So if we look, with that dilation, we start to fill in what should be beta, right? So I don't really quite like the fact that we did that we start to mess up our nice alpha and beta segmentation that we worked so hard to get. So instead of just closing this, what we're going to do is use this as a mask to our original alpha. So if we take this alpha segmentation, it's a little bit dilated, but that's fine, and set it now as our companion. And call our alpha back again. And so it's the same idea. Now this mask distinguishes primary alpha from secondary alpha. And this segmentation defines the true edges of the primary alpha. So if we do an intersection, it's like that. We retain our initial edges, and we have our secondary alpha, or our primary alpha collected. And now it's not 100% perfect. There may be tiny pieces here and there that got cut away that shouldn't have. But when talking about absolute large percentages across the entire image, small little cuts like that won't be terribly detrimental, especially because they move in both directions. Here is a little bit of secondary found as primary. Here's a little bit of primary is found as secondary. So this is going to be accurate enough, I think, for our purposes. So we have our primary alpha here. We'll set that away, call back our original, and subtract the primary to get the secondary. And there we have it. So this intersection now is our primary alpha, and this is our secondary alpha. Now, if we run our area fraction, we have the beta in our primary, in all of our alpha, and then we have the fraction as primary and the fraction as secondary. Now, the last thing that we wanted to get was the grain size of the primary alpha. And I guess we would also perhaps want the thickness of the secondary alpha. So to get the grain size of this primary alpha, what we can do is just chop these grains up with our separate features. So separate features, say threshold of 1. What does that give us? Okay. And it might be a little bit overzealous. Not much, but a little bit. So if we change our reduce our separation here some, Okay, and maybe set it up to 9. Yeah, that looks a little better. Okay, and now this will be our layer, primary alpha. Grains separated. Now we can measure the grain size of this. So if we do our measure features on the grains separated, if we get equivalent diameter and eccentricity, for example, there we are. And we actually don't need the area fraction of that particular measurement. So want the area fraction of all the others. Okay, here we are. Now to get a thickness measurement of the secondary alpha, I've tried to get these grains all separated cleanly, but with some of the more complicated parts of the structure, it just doesn't want to cut nicely with just the separate features. But that's okay. You can get a nice thickness measurement without having to separate all these grains using our local measurement tool. So what this is going to do is draw a skeleton through the image and then measure the thickness at each pixel along the skeleton. So if we look at these skeletons, we'll pick one that we like. This one's trim some of these tiny edges off a bit. Okay, there we are. And now we can generate a thickness measurement. And here's what we have. The thickness of each one of these lats here. And, excuse me, the thickness of each pixel along the skeleton of these lats. And so that's the end of our characterization of this image into primary and secondary alpha. Our topic next time will be characterizing an image by multiple segmentations. So we'll have an image with multiple overlapping different types of features all in one image, and using one segmentation, one layer, as the data for another segmentation. So it'll definitely be a fun recipe that we put together. So I'll see you then.